Hello everyone, welcome to our talk on mobile app hardening against reverse engineering. Before starting the talk, I would sincerely like to thank the organizer for organizing this conference and giving us a chance to present over here. Alright, so let's get started. A quick introduction about us. So myself, Vikas Gupta. I have been working at Thales TIS as a security researcher. I have a master's in information security. I have been contributing to OWASP MSTG guide. My co-presenter Gautam, he has been working with Thales TIS as well. He's been speaking at various conferences including Android Security Symposium in 2020 and SINCON 2020, that is last year. He enjoys cryptography and hardening mobile application. So a quick overview what is coming up in this presentation. So our main goal today is that we want to talk about how to harden mobile applications against reverse engineering and without using commercial tools. So we'll talk about that there are many commercial tools, but there are a lot of things which can be achieved without using them by some small steps and small configuration changes by the developers themselves. They can harden the applications. We'll talk about what is mobile app hardening, just to be clear and to avoid any confusion, because hardening as a term is used in multiple ways. We'll talk about various hardening techniques ranging from build settings, code hardening, data, cryptography. Then we'll have a quick case study on R2Pay, which was the CTF challenge in R2Con 2020. And then we'll have a discussion and we'll conclude our presentation. Okay, so app hardening, but what was the motivation for this particular talk? In our personal experience, we have seen that a lot of developers find it pretty hard, or there are not many resources to train them about how to go about security development. Our experience is confirmed by this particular paper, which was published in 2016, and in their survey as well, they figured out that the programmers don't have many resources to learn about application security. And so we said, why not we share our experiences about mobile app hardening, which we have been doing at Thales TIS for various of our products, and share with the other programmers so they can learn from it. So what is app hardening? So app hardening can be used in multiple contexts. For example, hardening against exploitation, which includes including stack canaries or position independent code. Then in terms of mobile applications, often RAS obfuscation is used in the context of app hardening. Overall, for us today, the idea is that we need to ensure the security of an app even on a hostile device or a breach device. So in this presentation, we'll be concentrating on app hardening against reverse engineering only, and we won't be covering the other various uses of hardening which are there. Okay, and we'll try to cover both the static and the dynamic analysis part of app hardening. So to understand that how we can really protect the mobile applications, there is this particular onion diagram. You can see that there are multiple components which can be implemented to secure a mobile application, or multiple steps or approaches which can be taken. So of course, secure design is the core of it, which can be having proper privilege separation or having the right designs for the protocol and things like that. Like, things should be secure by design. Then secure coding, which includes, for example, proper memory management if you're writing code in C, C++. If you're using Java, then serialization, deserialization. So things like that, which are inherent to the language to ensure that there are no vulnerabilities in the code. So that's what we understand with the concept of secure coding in this particular diagram. App hardening we will be covering in this presentation. which is about having extra features which can make reversing or breaking the application a bit difficult. In-app protection, I think who are aware with the mobile ecosystem, mobile application ecosystem, in-app protection or RASP, they're commonly used, means the same thing. It refers to having self-defenses, for example, detecting whether a device is jailbroken or rooted, if there's a hooking framework present in the process memory, or whether the application is being running in an emulator. So you can check for these parameters like jailbroken, emulator, or hooking detection or debugger detection, and then react accordingly. So that what comes under in-app protection. And of course the last one is software obfuscation. So it is like having control flow obfuscation, opaque predicates in your code, so that understanding and reverse engineering the code is difficult. Now the question arises, who needs app hardening? So to determine this, threat modeling is very important. If there is a no threat model, then it's hard to objectively answer the question that do someone need the app hardening or not, against reverse engineering particularly. So for example, if your threat model doesn't have a risk, or it's not a sufficient high level risk that reverse engineering is a threat for your application, then you don't need to harden against reverse engineering of your application. And so in our experience, whenever there is a critical business assets or sensitive services involved in an application, then you do tend to need hardening against reverse engineering. I mean, reverse engineering do become a credible threat in those situations. So for example, some very sensitive IP is there which is being included in your application, so you surely wanted to protect it. Similarly, if some, for example, government services are there now, digital identity is being provided via mobile applications like digital driving licenses. So in those cases you need to have some kind of reverse engineering protection to ensure the integrity of the content as well, and the whole application, of course. As I mentioned in the starting of the presentation, there are a multitude of commercial tools which are providing app hardening. Now, in industry, again, app hardening is a very broader term. It includes in-app protection, code obfuscation, symbol obfuscation. There are multiple commercial tools which we are not really concerned in this presentation. But the techniques that we will be presenting today may not be covered by the commercial tools. I mean, for sure we know that some of them are not part of the commercial tools, and even if it's there, I mean, whatever we are doing will only complement the whole development process. Generally there is no I mean, it doesn't break the things if you apply own app hardening and then you apply another commercial tool on top of it. So it's not the changes are not breaking things when you're using other set of techniques as well. So the goal for us is to protect or to slow down the reverse engineering attacks, and whatever ideas we will be presenting today are language agnostic unless we mention it. And I mean, we will be using the examples from certain set of languages like Java or Objective-C, but you will see that the overall theme would be applicable even if you're developing in some other language which apart from Java, Objective-C, Swift for example, or Kotlin, or even C# using Xamarin. So the ideas are still applicable. So to just set the tone, there are two basic approaches for reverse engineering. One is static analysis, one is dynamic analysis. Now in static analysis you are not really running the binary while reverse engineering a binary. You just try to understand what possibly the binary is doing by just looking at the disassembled code or decompiled code using the tools like JADX, IDAPRO or Ghidra. In case of dynamic analysis, you run the binary and then you see the outcome, whether it is the data or whether you see how the information is flowing through the binary. You can use various set of tools including debuggers, and then you have this awesome tool Frida, edexposed, So yeah, that is the major two approaches, and our goal is to both slow down reverse engineering using both the techniques, static and dynamic. So you will see that the techniques that we are discussing today, one way or the other, do target yeah, static or the dynamic analysis. Okay, so let's get started with the technique. So first for us is related to the build settings, and the first of them is stripping of symbols. Now yeah, most of us would be stripping the symbols for the basic need that by removing the unnecessary or not needed symbols, you reduce the size of the binary. So that is one of the common cited reason, but then we'll take a step ahead that yeah, having these unnecessary symbols which are not needed for the execution of the binary leaks the information about the code, and that helps in reverse engineering. So our goal is to minimize this information. Now I have a snapshot from an application which is an iOS application in production on the App Store, Apple App Store, and you can see there are debug symbols over there. And for example, decrypt string looks pretty interesting, that it hints that yeah, this particular application or framework is having encrypted or obfuscated strings, and then you have the functionality to decrypt it. Why not attach a debugger over here and start seeing what's going on? Similarly, if you have used the tools like APK-ID, they tell us about what compiler is used or what obfuscator is used, but then it's important to understand that this information which APK-ID is extracting, it is from the binary itself. So in case of ELF binary, there is a lot of information in comment or string tab, sim tab section. So if we can strip these sections off, then effectiveness of APK-ID reduces, and then basically it helps us in slowing down the attackers. I mean, they have to use different techniques to figure out the information. Visibility hidden flags. So as I mentioned with stripping, that you don't want to have symbols or information which is not needed for execution. So actually when you are building a shared object or a binary, especially on the native side, yeah, which is C++ code, that lot of the symbols which are private to the shared library are exported as well, or are present as well. So over here in the example, I have the Facebook Android application, and you can see it's yeah, it is having a lot of EVP symbols which is coming from OpenSSL. So Facebook do use OpenSSL, and from our experience we have seen that EVP symbols don't need to be exported. So if these symbols are not exported, it should not hamper the execution of the application at all. So you can remove them basically. And how to remove them? So you can set a simple compiler flag with the f visibility equal to hidden, and it will make all the symbols hidden by default. Now with having all the symbols hidden, it affects our symbols which genuinely needs to be exported for the proper functioning. So there's this additional step that you need to mark all these symbols which are supposed to be exported manually with the attribute visible. So yeah, we will be talking about this particular attribute later on in crypto as well. So the idea is that yeah, don't export or make the symbols which can be hidden or private available in the final binary. Just remove them. This is just additional information helping the attackers. Then static linking the library. So static linking over here we are not using in the strict sense, because we will be applying for Java as well. But you get the idea that what we are trying to achieve over here is we want to have one big binary, monolithic binary, having minimal symbols, and which really makes hard to reverse engineer the binary. Now what we really mean with minimal symbols is that if there are not multiple shared objects, then those shared objects don't need to export the symbols. And if it is statically linked, then compiler will just take the addresses and link the source code or the final binary using this addresses. So let's try to see this with an example. Again, it's not called static linking in case of Java, but yeah, it's easier to get the idea that what we are trying to propose in this one single heading of static linking. That what we're trying to achieve over here is, yeah, instead of yeah, on the left hand side we are using the system APIs for performing certain operations, and on the right hand side we are using Bouncy Castle. Now Bouncy Castle is compiled with the source code, so not as a third party dependencies, but with the source code. And what advantage do we get? So once we run the ProGuard on it, everything can be obfuscated. So you can see that the same code, when it's compiled and ProGuarded, that particular function names and API names are no more present in the binary. And similar things happen with the native code as well. We'll have example of native code as well later on in the presentation. So yeah, for now we use the Java one. Yeah, I think this is the most common one, symbol obfuscation. I think everybody understands this, but I just want to highlight one additional point, that there are places where you tend to keep meaningful symbols, or the tools cannot reach there to obfuscate it. So over here I have an example from Barclays Android application. You can see some JNI symbols which are there. They have been obfuscated, pretty much meaningless. Although in this case I'm pretty sure some commercial tool is being used to obfuscate, but you can do this thing on your own as well. You not necessarily need to name the symbols which are meaningful. You can always name the symbols with something meaningless, like the one that you're seeing over here. So do keep in mind that yeah, there are places where the common freely available tools cannot reach, and where we can obfuscate them manually. Let's move on to the next part, code hardening. Now this is a common mistake that we do tend to see, and in a sense it's a good coding practice as well, and that's why it happens. So a lot of functions which are like is jailbroken, is hooking, so they tend to return Boolean values. But the problem with Boolean values is that it's very easy to patch them or hook them and replace the value. Even it's very easy to understand the logic as well, right? If something true or false is being returned, you know that yeah, there are only two ways this function can return, and you can just flip the values to figure out, okay, which one works for me. So in this case I have an example from PayPal iOS application, where the logic for SSL pinning is using a Boolean return value, and it's pretty easy to just flip the thing. So one way is that I can just remove the whole function BL and just have a value where x0 is 0 or 1 depending on whatever the logic is, or I can use Frida and just couple of lines of code and say that okay, flip the value, always return this thing, and yeah, for me that particular protection has been bypassed. So that's a problem with having simple Boolean values. Now look at this example. So it will help us in solving two particular cases that I want to talk about. So firstly, let's look in terms of whether it's a Boolean value or what kind of value it is. So surely the return value which is there in x0 register doesn't look simple. I mean, for sure it's not Boolean. And you can see that I have three screenshots. These are three instances of running the same function, and the return values are different. And yeah, basically whenever you run this particular function, the return value will look different. Now it solves two purposes. Firstly, I don't get it whether it's a true or false or some other value being returned, and then secondly, okay, I mean my common instinct is that okay, it's not a simple value, let's just replay it and try to figure out what's the one that works for me, like in the clean environment or with the jailbroken environment, things like that. And you can see that even the replay won't work because every time the value being returned is different. So this is a nice way to protect your functions, like especially the critical ones which you feel that should be protected, and will surely slow down the attackers if they cannot figure out what's going on. So this is a pretty neat way. System APIs, so I did touch a bit in the previous screenshots or the example I was showing. So the idea over here is that from a reverse engineer's perspective, the attacker's perspective, you look for things which you can understand. For example, string compare, mem copy, or if you're looking at the Java code, you look for crypto, key store, things like that, like where it is likely to give you a good results if you start hooking or reversing that particular part of code or piece of code. So we propose that instead of using the libc code or whatever, I mean, if it's a lib system in case of Objective-C, use this instead use the custom code. So what I mean by custom code is that, for example, string compare, use the code from the libc open source libraries which are there, like muzzle, and copy it in your code and just call that particular function. So the string compare function or the symbol won't be there. And similarly, you can have the syscalls. For example, if you want to read or write particular files, instead of calling read or write via libc, why not have it via syscalls? So those symbols won't show up in the library or the final binary. So I have some examples for you. So on the left hand side is the case where I copied the memset and the string compare functions into my own source code, like my application source code, instead of using the libc. And on the right hand side is the case where I'm trying to use the syscalls. And for sure, I mean, later on we'll discuss with R2Pay as well that these things do slow down the analysis. You need to figure out where those functions are or what exactly the logic is, and especially if you're inlining these functions, then it becomes harder and harder, because the size of the function increases and it's pretty difficult to figure out what's going on in these functions, or requires more effort. Again, as I mentioned, you can use reflection in case of Java, so it doesn't show up in the import part of the Java classes, because often that is a place where you're looking for to understand what this particular class could be doing. So for example, if you have a lot of crypto and key store related imports, then you are sure that something or some meat is there, like something important is being done over there. There's a catch. If you're using reflection, then you need some kind of string obfuscation, because in the reflection itself, the name of the class or the function name would show up as a string. So you need to do string obfuscation over there. Okay, now data structures, especially the string ones. So we have seen that, or I think most of us are aware that if you're using immutable data structures, then handling their lifetime becomes slightly tricky. Now, for example, if there's a string containing a password or some other critical information, once the password is used, you cannot easily destroy it, because if you want to overwrite that particular password string, then a new string would be created. The data structure is immutable. And that's where the problem comes in. You need to depend on the garbage collector or reference counting in case of Objective-C for this particular function variable to be destroyed. So what we propose is, why not use byte arrays? Now with byte arrays, the advantage is that you can change the values whenever you want. So for example, in the start there was a session key in there, and once you figured out that we have used the session key, you can zero it or replace with some random values, and then you are sure that this particular variable is not hanging around in the memory for a long time. So that's one way to ensure, like, no critical value is in the memory for whatever duration, or the minimum duration is needed, no longer than that. In the same idea that I just mentioned with string data structure or immutable data structures, in general also try to reduce the variable's memory lifetime, irrespective of the language. I mean, whatever language you're using, try to zero it or set some random information in those set of variables once they are used. Similarly, mark the sensitive values when in the memory, mask the sensitive values. So what does masking mean? For example, there is a particular session key, for example, that will be used multiple times in a particular session or in a particular time window. So you cannot always be zeroing it and resetting it, and also why not have another XOR value or a XOR byte array, and just keep it masked with this particular, by XORing it, this particular byte array, and when you need it, unmask it, use it, And once it's done, then zor it back again. So yeah, you can do this process as many number of times whenever is needed, and it ensures that the information is not there in the memory for long duration. Okay, data hardening. So there are two ways where data is there, like data at rest and data in transit. We'll talk about both of them. So data at rest, yeah, you try to ensure that the data itself is not leaking information, like the labels that you use to point out to the data. So I'll show you an example. This is the case of Google Authenticator, where if you open up the SQLite database, you will find that the database columns have pretty meaningful names like email, secret, counter, so you know what you're looking at. But if you look at the example right at the bottom, the data itself is encrypted, and the column names are also meaningless. So we can see it ourselves that the case at the bottom one is much harder to understand or to reverse engineer, and that's the goal. Like, don't leave meaningful names for your data. Data in transit. So this includes while going over the network, for example, and the goal over here is that don't put meaningful names to the keys which are used. For example, in case of JSON, the keys can be very meaningful, like in this particular example that you have OTP, phone number, IMEI, so you very much know what's going on. So if you have some meaningless names, then it would become very much harder for the attacker to figure out what's happening in there. Alright, so now I'll hand over to my colleague Gautam to take us further with the other topics. So,
Thank you, Vikas. Hello, everyone. I'll be discussing about crypto hardening. Application uses cryptographic algorithms to protect sensitive data in the application. So in this section, I'll be discussing about simple techniques that can help to make it harder for a reverse engineer from doing static and dynamic analysis. The first thing is about inlining sensitive functions. So when you inline sensitive functions, even for a cross-referencing, it is very difficult to do. There are compiler directives to make it forcefully inline certain functions. So when you can actually have sensitive function as a separate function, but ensure to give this particular compiler directive so that this will be taken care by the compiler. Sometimes the compiler might not really inline those functions, so it is through an iterative process that you have to reverse and find out that the specific function is inlined or not. Let's switch to system APIs. Application uses system APIs for performing cryptographic operations. But the downside of that is when you use system APIs, it becomes difficult to obfuscate them. So we propose here to use third-party libraries and statically link them. For example, on iOS, you can actually use OpenSSL or any other popular native cryptographic libraries and package them along with the source code. So you have to link it statically so that the symbols are gone. You have to build them with visibility hidden so that the symbols are gone. So instead of using CC cryptographic common crypto APIs, so using a third-party APIs is beneficial in terms of a reverse engineering perspective. So here the snapshot shows two different things. The first, on the left side, actually we have built an embed TLS cryptographic library with visibility hidden as false. So on the final binary, you can easily figure out that this specific function is in fact doing AES GCM operation. On the right side, just by having a visibility hidden as true and statically linking with the original binary, so you can have this symbols getting stripped off and only the addresses remain here. So by seeing just this specific function, it is very difficult to infer that it is in fact doing any AES or GCM operation here. On Java side, we can actually use Bouncy Castle library and package them as part of your application. So instead of using system APIs, you can actually directly call the bouncy castle APIs and make sure that you don't call these APIs via a Java provider route. So here is an example which we have used. So on the system, we are trying to do a HMAC operation. So this particular function is performing a HMAC operation using system APIs. On the right side, it is using the bouncy castle APIs. So let's see how it shows up in the final binary. On the left side, you can see the imports because this is using the system APIs, and also the actual calls to the HMAC operation is very much visible on the binary. But rather on the right side, if you have used bouncy castle and with ProGuard, all the functions can be nicely obfuscated, and it doesn't give any trace that it is using any cryptographic operation here. The other important aspect when you use cryptographic algorithms is crypto constants, because crypto constants is one of the ways reverse engineer can trace back the original calls to the cryptographic APIs which is used in the application. In this example, we have taken SHA-256. So SHA-256 uses one of the crypto constants called K constants, and this K constants is used by SHA-256 block data order API. This block data order is actually referenced by multiple other SHA-256 functions, which in turn leads to the APIs which is actually used by the application. So the moment you are able to trace the crypto constants, you can trace it back till the API which is used by the application, and from there you can actually even get the data being passed to these cryptographic algorithms. So we have used a Facebook application where it uses SHA-1 and SHA-256 in one of its native libraries. So we did this exercise of dumping the crypto constants, and from there finding the SHA-256 block data order API, and from there you can actually trace the other the APIs leading to the cryptographic APIs called by the Facebook application. So likewise, you are able to trace the SHA-1 update from the once you get the key constants there. So for as a mitigation aspect, so the important thing to note is you can actually obfuscate these crypto constants with some arbitrary constants. But it is not enough, because when you do this, compiler might do some optimization and bring it back to the original constants. So you may need to have additional effort, like making it volatile data so that it is not easily optimized by the compiler. So this is at a compile time, use a different constants, and at runtime you should get back the original crypto constants that can be used by the crypto algorithms. So when it goes to critical code, so especially crypto being a critical thing, if it is in the native, it makes it harder for any reverse engineer. Our proposal is actually to make use of all third-party cryptographic libraries like OpenSSL, embeddTLS, and for that matter, you can actually use any native cryptographic provider. But the most important thing is you have to build them with visibility hidden and link them statically. So even if you have done all these things properly, it still is vulnerable for certain reverse engineering attacks. For example, so we can actually do some sort of heuristic mechanisms to compare the algorithms, so to identify what exactly this particular function is doing, even though the symbols are stripped off. So besides that, there are crypto constants can also indicate some matching functions. So in this case, we actually propose open source tool called obfuscator LLVM to obfuscate the control flow and protect the strings to protect against some from diffing or pattern matching tools. To showcase this, actually we built two libraries, one with visibility hidden set as false, so that it shows all the functions of the embeddTLS. So it just exports all the functions here. On the other library, when all the symbols are stripped off nicely, and I now compare these two libraries in a bindiff2. So now I can see an equivalent API for this particular address, what exactly is the API. So with bindiff, it is quite easy to figure out what exactly the function is being used, even though the symbols are stripped off. Uh, by just seeing the similarity and confidence, it just indicates this is more or less the same function which is being used in this binary. So from then onwards, you can actually start hooking them to do some sort of dynamic analysis and start fetching the keys which is being used for the AES operation here. So the mitigation for this is to actually use an obfuscator. So using an obfuscator like OLLVM can actually make it bit harder to actually match it just exactly like this using bindiff tools and all. So now let's talk about RASP. So when we talk about mobile app hardening, usually the discussion starts and stops at RASP. RASP is actually a good starting point, but it is not always sufficient. Because the RASP, usually apps integrate RASP libraries as mutually exclusive ones from that of the actual app logic. When it is integrated like that, it is quite trivial to bypass RASP detections and get into the core logics of the application. So it is just a few little effort it will take a reverse engineer to actually get remove all the RASP detections and start focusing on attacking the actual core logic of the application. So our general proposal when we use RASP techniques is like it is just integrating RASP libraries is not enough. So you may need to still follow some sort of additional hardening that we have discussed before to ensure the RASP techniques are not easily identifiable and easily reversible. So generally, this will generally enhance the overall RASP protection also. So as a case study, we are going to discuss about R2Pay. R2Pay is an application which we developed for a CTF in R2Con 2020. So this is developed along with now secure researcher Eduardo Novella. So we did this last year by making use of all good techniques that we have discussed in this slides here. So in this R2Pay, so what is actually done is there's a code obfuscation using ProGuard for Java, and for C we are using OLLVM obfuscator. For code hardening part, we are inlining most of the sensitive code. For libc APIs, we are replacing it with custom code and some file operations with syscalls, and also they are inlined as part of the original logic. We also introduced a lot of RASP techniques, and these RASP techniques are also inlined as part of the core logic. So as a best practice, we used byte arrays and avoided strings, and we used to wipe the memory after using some of the sensitive crypto keys there. For a crypto obfuscation, so we ensure that the symbols are removed, so it doesn't give any trace of which cryptographic library we are using. The crypto constants are also obfuscated, and it is derived at runtime from arbitrary constants. So by using sign search tools, so you cannot easily figure out the crypto constants from the binary. So as an advanced level, we actually used white box cryptographic to actually hide the cryptographic keys, which depends on the threat model of your application, whether you really wanted to do white box cryptography or not. So for a demo, so I'll be showing the R2Pay application from a reverse engineering perspective. So here you can see we use ProGuard, so you can find all the classes and methods nicely obfuscated everywhere. And from we didn't really do any string encryption here because there is no sensitive data actually on the Java side. So the most sensitive things are actually happening on the native part. So the native call is going via this particular exported API. It doesn't reveal what exactly it is doing. So let's switch to the native part. So I'm using IDA Pro for showcasing the native library, which is used in the autopic. So from exported things, so this what we wanted to see is we are not really exporting any APIs, especially the ones which I showed on the Java side. It is in fact loaded dynamically on the onload part. So that particular API is not visible, so it cannot be directly hooked to see what is the data coming inside the native library or not. The remaining sets of exported things is coming from the OLLVM obfuscator. By just hooking them also, you may not be able to figure out what exactly is happening. So now the next thing is to see the strings. So we relied on open obfuscator LLVM to actually obfuscate most of the sensitive strings. So whatever is readable, which you see here, is from the libc, but the remaining thing is mostly nicely obfuscated by the tool. So another best practice is to actually we did a best effort to actually use open source custom algorithm, custom logic for replacing the libc calls. So for file operations, we used syscalls, and for some of the memory operations, we had a custom code and inlined them nicely. So you don't find those things on the imports of this particular library. So since we used syscalls, so I just want to show you that we used around 10 to 15 calls to the syscalls. But because of the obfuscator, it has just exploded exponentially here, where you can see around 200 plus syscalls being showing up. So it will definitely take quite a number of time to figure out where exactly this syscalls are being actually being used, and what exactly we are trying to do with all these file operations here. And from a control obfuscation point of view, so the OLLVM as well as inlining of the code makes it even more harder for somebody to find out a single function properly, because a single function is the control for graphs is quite huge enough to actually start reversing that, because there are too many inlining is happening, and obfuscator makes it even more worse in terms of reversing this specific function here. From crypto constants perspective, so I'm using a sign search on this specific library, and you can't find any signatures, any crypto constants that is present on this native library here. So this overall, actually, this is like whatever the techniques which we have discussed is actually incorporated as in this particular application to showcase how difficult it will be on the final binary. So to conclude, so we discussed what is app hardening and its importance. So we also discussed different hardening techniques for in terms of build settings, code hardening, data at rest and data at transit, and crypto hardening. So we showed as a case study on R2Pay how these techniques translate into the final binary. So what you have to note is one technique in itself is not sufficient. So use all of them for maximizing the benefit. Also, it is not a one-time thing, so it is an iterative process that you have to keep improving the code. But finally, it all depends on the threat model of your application, and include them as and when it is important that you have to obfuscate certain portions of the code. Thank you for this opportunity, and thank you organizers for conducting this awesome conference, and thank you for providing us opportunity again to present here. Thank you. Bye-bye.